All right, lads and ladies, welcome back to pre-calculus. Congratulations on surviving the second exam. Today we are going to move forwards and shed the shackles of polynomials and start talking about a whole new family of functions. So those of you who have just had it up to here and beyond with polynomials and rational functions and all that shit, deep breath. We're moving away from that stuff. Today we begin talking about what are called exponential functions, and I'm going to introduce those through an example. We'll play around with some graphs and stuff like that. Your tests, I know everybody wants the test back right away. Everybody wants to know how they did. It's going to take me some time. I'll do my best to get them graded within a week. That's usually my rule. Unfortunately, with the testing center and people taking tests on so many different days, I have some folks who haven't taken the test yet are going to take it on Friday because they missed the test or whatever. Might be a little bit longer, but I'll do my best to get your test back to you within 1 week of the day you took it. Get the store closed so I don't wake up the baby. And turn on the screen share and we can get moving. Oops, I'm gonna pop this. Okay. I have a favorite way of introducing exponential functions because I'm old and a big fan of John Steinbeck. I'm just curious. I always like to ask this because it helps me get a feel for what's going on in high schools these days. How many of you have read the book Of Mice and Men? Steinbeck. Just give me like a thumbs up react or any react in Zoom if you were made to read the book Of Mice and Men or chose to read it at some point. John. Okay. I'm sure all of you have seen the cartoons where somebody is chasing Bugs Bunny and he goes, "Which way did he go, George? Which way did he go?" All of those are references to this really great old book by a man named John Steinbeck, written during the Dust Bowl in the United States, a time of great poverty and workers sort of slowly building up their rights. Well, good. I'm glad to hear that Megan has read it as well. If you haven't, it's a short book and it's really engaging. I promise you, if you pick it up, you will finish it that day. So I'm going to make a small reference to that today. This, of course, is MAC1140, section 008, which is a pre-calc class. And today is the 28th or 27th? 28th of October, 2021. Today, as promised, we're starting on exponential functions. The path from here, we're going to talk about exponential functions today. I will introduce a special kind of exponential function in our next class, which for you guys will be next Tuesday. Then we're going to introduce logarithms, which are the inverses to exponential functions. So all that stuff from section 2.8 on inverse functions, it's coming back. So be ready for that. If you didn't study 2.8 back then, you may want to put some time in between now and then. And then we're going to talk about some properties of logarithms and exponentials, how they interact with each other, and we're going to use them to solve equations that previously we couldn't have solved. And then we'll be ready for test 2. So there's this gap between test 3. Be ready for test 3. The gap between test 2 and test 3 is very short. This is just like 4 or so sections, and they move quick. So we're talking about test 3 being maybe a week and a half, 2 weeks. Just give you a heads up. Okay. Other stuff. Not so many stuff. Not really. I'm going to publish a new homework for you guys today. I promise it's an easy homework. It'll go quickly. And it will be due on Tuesday of next week. So you want to be putting some time into that between now and our next class. Like I said, I feel the best way to introduce these is through an example. Exponential functions are beloved by mathematicians, biologists, physicists, anybody who uses math, because their mathematical properties are very nice. And also they show up in real world situations like you wouldn't believe. If you've ever watched physics lectures or any sort of discussion of any sort of real world hard science, inevitably you will bump into the discussion of exponential growth, exponential decay. If you watch the news, you'll see people misuse these terms all the time. So you'll now be ready to say, "Oh no, that's not exponential. That's polynomial," or something like that. But here we go. In the Book of Mice and Men, George and Lenny, their goal is to get a farm, right? And Lenny, big, goofy, not super intelligent, but very physically powerful man, wants to take care of some rabbits. So I'll say on day 0, Lenny has 1 rabbit. And he found it on the side of the road, whatever. On day 1, George gives Lenny another rabbit. And warns rabbits, being rabbits, doing what rabbits do, he warns that the number of rabbits will double every day after that. Okay, it's a mild exaggeration, but I'm doing this to make the mathematics a little bit easier for us. So of course, rabbits don't double their population every day, but you know, rabbits are rabbits. You get more rabbits, that's how it goes. So on day 0, Lenny has 1 rabbit. On day 1, George gives Lenny another rabbit, so he has 2. And every day after that, the number of rabbits will double. We want to find a function. I'll call it f of x. Which tells us the number of rabbits on day x. And we're going to do this by making a little table. Oh, sorry, one second, guys. Okay, so I think the easiest way to do this, if you haven't seen it before, is to make a little table and start trying to come up with a guess. It's like one of those what comes next puzzles that your aunt posts on Facebook and says only 5% of people can solve. So we'll put the day over here and the number of rabbits over here. We're told that on day 0, Lenny has 1 rabbit. So when x is 0, f of x is 1. In other words, f of 0 is 1. On day 1, George gives Lenny another rabbit. So on day 1, Lenny has the rabbit from yesterday and also the new rabbit that George gave him. So he has 2 rabbits now. How many rabbits does Lenny have on day 2?
4.
Yeah, because every day the number of rabbits is going to double. So as we go up 1 day, we double the number of rabbits. What about on day 3?
8.
Very good. And on day 4?
16.
16. So the nice thing about this behavior where you're doubling so often is that it can be described algebraically really nicely. What do you notice about the numbers in the right column here?
They'd be even besides 1.
Certainly they're even, right? Even more special than that, notice we skipped 6. Sorry, we skip over 6 here, right? 6 is an even number between 4 and 8. And we skip over 10, 12, and 14 here. So not only are they even, what else can we say?
Aren't they all factors of 16?
They are all factors of 16. And another way of saying that is that they're all powers of 2, right? 16. Let's start here. 2 is 2 to the 1. Maybe a different color. 4 is 2 times 2, or 2 squared. And to go from 4 to 8, we multiply by 2 again. So that's 2 cubed. and 16 is 2 to the 4. And even better, 1 is 2 to the 0. Remember, anything raised to the 0 power is 1. Do you see a connection between the left column and the numbers on the far right?
They're inverse of the function or the exponent.
I wouldn't use the word inverse here. But if you had to, looking at the orange numbers on the right and the purple numbers on the left, tell me what goes down here in row X. What would you say goes right here? Thinking of the orange numbers.
X to the power of n.
No n's here, but the 0 to the 0, 1, 2 to the 1, 2, 2 to the 2, 3, 2 to the 3, 4, 2 to the 4, X.
Would it be 2 raised to the x?
Perfect. 2 to the X. So f of X, the number of rabbits on day X, is 2 to the X. And while it might not jump out at you right away, this is very different from any of the functions we've looked at before. See here, the base is a constant. We've seen lots of things like x squared and x to the 1/3 and stuff like that, where you've got your variable raised to some constant power. But here it's the other way around, and maybe that's what you meant by inverse. I've got some constant power, or some constant raised to a variable power. And that's sort of, in a sense, the opposite of what we've seen in the past. Precisely that feature, that you've got a constant raised to a variable power, is what makes this an exponential function. And before we talk more about that, I want to just look at the graph of this function. We've got a table here, we might as well draw a graph. And call this 1, 2, 3. And let's see, the biggest output I actually found there was 16. So we'll call this up here 16. And so 8 is halfway from 0 to 16. This would be 8. 4 is halfway from 0 to 8. So we'll call this 4, which makes this 2 and makes this 1. So if we plot these points, 0, 1 is right here. 1, 2 is right here. 2, 4 is right here. 3, 8 is here. And 4 would be like here. So 4, 16 is up here. So this curve kind of looks familiar, right? If we start like this. The next point, if I kept going here, would be 5, 32, which would be like way up here. And since I don't have the space to draw that, I'm just going to do the normal thing of putting an arrow like this. If you were to follow this pattern, but plug in some negative numbers, like -1 and -2 and -3, 2 to the -1 is 1/2. So this guy would be like right here. 2 to the -2 is 1/4, which is already too small for me to see on this scale. So I'll just, and 2 to the -3 would be 1/8. So this function is doing something interesting. As we go off to the left here, this is getting very, very close to 0. If we want to add a few values to this table, we can. So -1, you have 2 to the -1, which is 1/2. With -2, you have 2 to the -2, which is 1/4. When x is -3, you have 2 to the -3, which is 1/8. And since 1 is right here, 1/8 is like 1/8 of the way up. It's so goddamn small, I just don't have room to draw it. But what you notice about these numbers, this is 0.5, 0.25, what is 1/8 as a decimal? I feel like 0. It's embarrassing. 0.125. Yeah, 0.125. These numbers are getting very, very small. They're getting very, very close to zero. Remember, 1 over a big number is a small number. We learned that when we talked about asymptotes for rational functions. So 1 over 8, the next guy would be 1 over 16, and then 1 over 32. As those denominators get bigger and bigger, these numbers get closer and closer to 0. So this function does have an asymptote. It has a horizontal asymptote, and it's the line y equals 0. And it only approaches it on the one side, which is kind of neat. Rational functions didn't do that. This is what the graph of pretty much all exponential functions look like. And I'd like to take note of some features of this graph, starting with things like the domain and the range. Okay, so if this piece continues over here forever and ever and ever, just getting closer and closer to the line y equals 0, and this piece continues over here forever and ever and ever, just going over and up, what's the domain of this function?
Negative infinity to infinity.
Very good, all real numbers. Negative infinity to infinity. You can plug whatever number you want into here. No problems. You're never going to divide by 0. You're never going to take a square root of a negative, anything like that, right? There are no domain red flags here. What is the range?
Would that be 0 to infinity?
Perfect. Yeah, exactly. The range here is the open interval from 0 to infinity. And there's some interesting stuff to take away from this range. Something like 2 to the x could never be negative. There's no number x you can plug in, here that will make this negative. In other words, no matter what you raise the number 2 to, you're never going to get a negative number out. Even if you plug in like negative 1 million, you'd have 2 to the negative 1 million, which is 1 over 2 to the 1 million, which is an extremely small number, but it's still positive. You'll also never get 0. Right? No matter what you plug in here for x, you'll never get 0 out. This thing can get really close to 0, but you'll never hit 0, and you'll never dip below 0. So exponential functions like this, they're always positive, strictly positive, never equal to 0, never equal to a negative number. Okay. I claim that George and Lenny are in some pretty deep shit. I claim that even barring the sort of things that happen in the book, these guys are going to die soon because they will drown in a sea of rabbits. This function over here gets very steep. Right? Remember I said that the next point, 5,32, would be right around here. And the next point after that would be way off the page. So the first kind of big observation I want to make, besides this domain and range, which, by the way, these are the same for all exponential functions. And I'll give you a formal definition of an exponential function in a second, but the domain is always all real numbers. The range is always positive reals. I claim that 2 to the x grows much, much faster than something like x squared, x cubed, or even x to the 2021. Faster than any polynomial or power function. Basically, if you zoom out on the graph of an exponential function, they appear to go straight up. And then over here, they appear to turn around and go straight to 0. It's very dramatic. Let me show you. for you, and then we'll do some quantitative work. But first, just a quick look at the graph at qualitative assessment. Here's 2 to the x, looking an awful lot like we said it looks. You notice as you run off to the left here, we get closer and closer and closer to 0. Look how small these numbers are getting, the y values. But we never hit 0. No matter how far you go to the left there, you never hit 0. It does settle down closer and closer to 0. So these are functions which do not touch their horizontal asymptote. Remember, it is possible for a graph to touch its horizontal asymptote, but these guys do not. The thing I want to emphasize here, though, is just how fast these grow. Look at this motherfucker shooting straight up. It's because every time you take one step to the right, you double the height. So if you're right here, let's say 32, got 5, 32 right here. And you want to look for the next point on this graph with an integer value of x. It's way up here, right? F of 6 is 64, the double of 32. And if you want to look for the next one, he's not going to fit on the screen. I have to zoom out some more because he's not adding the same height again. He's going to double the height of the green dot. So he's going to be way the fuck up there. So you see this graph, it goes like straight up, really, really fast growth, much, much faster than, for example, x squared. Pick your favorite x value like 5 or 6 or 7, and the red graph is going to be way above the black graph. Here, let me look at the line x equals 7. Green dotted. Let's go to the stuff we don't need. Focus on this. All right, so the black is x squared. The red is 2 to the x. And if you look along this green line, the black is much, much, much smaller than the red. So the red function shoots straight up, and even as fast as x squared grows, and it does grow pretty quickly, right? This is pretty steep. The red is much, much, much more steep, like not even comparable. At x equals 7, the red is way up here. At x equals 7, the black way down here. Right, 7 squared is further down, 49 is right here. So 2 to the x grows much faster than x squared. And if you change that x squared to an x cubed or something else, it's still just totally dominated by this red function. It might take a little while, but totally dominated by the red function. If we want to be a little bit more quantitative about what it means to grow quickly, what sort of thing have we talked about this semester that has to do with how quickly a function is growing? What words might we associate with how fast a function is changing? Remember, I said this function goes like straight up. We're talking about slope or rates of change. When I say 2 to the x grows fast compared to x squared, I'm thinking about how steep the graph is. I'm thinking about rates of change. So the average rate of change for 2 to the x, and I'm just going to pick some numbers here, it doesn't matter, say from x equals 8 to x equals 9 is 2 to the 9 minus 2 to the 8 over 9 minus 8. Right? That's the average rate of change formula. F of B minus F of A over B minus A. Two to the 9 is 512. 2 to the 8 is 256. And 9 minus 8, that's just 1. 512 minus 256 is 256. So from x equals 8 to x equals 9, 2 to the x, as you take this one step over, goes up by 256. The slope for that function from x equals 8 to x equals 9 is 256. It's not a constant slope, right? Remember, that's the slope of a secant line, but that's the average rate of change. Compare that with the average rate of change for x squared over that same interval from x equals 8 to x equals 9. That is 9 squared minus 8 squared over 9 minus 8, which is 81 minus 64 over 1. What's that? 84 minus 64 would be 20. This is 3 less. This is 17. So the slope for 2 to the x from 8 to 9 is 256. That's how steep this motherfucker is. That's how fast 2 to the x is growing. On the other hand, the slope for x squared from 8 to 9 is 17. That's still pretty steep, right? If I give you a line with slope 17, you'd be like, damn, that's a steep line. But if I compare that to a line with slope 256, you'd be like, holy shit, that's not even close. This is what I mean when I say 2 to the x grows faster, right? Much faster, like orders of magnitude faster. And the bigger the x values are, of course, both of these numbers will get bigger if you use bigger x values, but the difference between the two will get more and more severe as the x values get bigger. So not only is this like a whole order of magnitude larger than this, if you were to look from x equals 80 to x equals 90 instead of from 8 to 9, this would be multiple orders of magnitude bigger than this. So 2 to the x grows a shitload faster than x squared. And we could play the same game with x cubed and x to the 4 and x to the 5. Sometimes the polynomial functions, these little power functions, will appear to grow faster at first, but any function like this will eventually overtake it and grow much, much, much faster. Okay.
Could I ask a question real quick?
Of course.
I know it's in my notes, but could you give me the equation for average rate of change again, just real quick?
Oh, sure. Average rate of change from x equals a to x equals b, that's f of b minus f of a over b minus a.
Thank you. Sorry.
No, don't feel bad. Yeah, that's fine. It's no big deal. Okay. So 2 to the x is not the only function like this, right? In the same way that x squared is not the only function like this. There's x squared, x cubed, x to the 5, x to the 1/3. There's 2 to the x, 3 to the x, 5 to the x, 1/3 to the x. We can play that same game with all these. The definition, what makes an exponential function an exponential function? A function of the form. Your book writes it as f of x equals a to the x is called exponential. the constant A is called the base. And we require A to be greater than 0. The base has to be positive. To see why we want A to be positive, imagine you tried to use just -1 or -2 for the base. If you start plugging in x values for like -2 all to the x, then when x is a fraction, like 1/2 or 1/4 or something like that, you're going to get i's out. So this is to avoid imaginary numbers. I can show you what Desmos tries to do if you ask it to graph an exponential where the base is not positive. It gets very confused. It's actually kind of interesting. We'll just change this to a -2 to the x. And the thing has pretty much shit its pants. Right? It's got no hope here. And the reason for that is, sure, you can plug in like a few numbers. But you get weird stuff out. Right? So when you plug in 0, you'd have -2 to the 0, which is 1. When you plug in 1, you'd have -2 to the 1, which is -2. When you plug in 2, you'd have -2 squared, which is 4. Things get really weird if you ask for like f of 1/2, undefined, because that would be the square root of -2. So it's an imaginary number, right? And way worse, like what the hell is f of pi? How you gonna raise -2 to the pi? Good luck. Good luck. So we will run into all sorts of weird things with imaginary numbers if you use a negative base. So anytime you're talking about exponential functions, you can assume that the base is positive. It's true. It's true. Desmos absolutely poops its pants. Sometimes Desmos tries to do stuff. I won't do this. Sometimes Desmos does make an effort with things like that, but here it's not even trying. The reason is that most real numbers, most possible inputs when you're looking at a graph, most of the x values are not integers. Most of them are like either weird fractions or irrational numbers. And raising a negative number to an irrational power is not a simple feat. Requires several years of complex analysis, I think, to really understand what's going on. At least one semester, not a simple thing. So exponential functions, as discussed in common world, even common math world, you're going to have a positive base. Okay.
If we were to see like a negative base on like a homework or a test, would that just be not undefined? But how would you just say that that doesn't work?
I promise you won't see it.
Okay.
Yeah, if you're to encounter something like that anywhere, then a mistake has been made.
Okay.
I think what I'd like to do next is to look at a couple more exponential functions and just practice evaluating them at different inputs to give you a feel for the sort of algebra and arithmetic rules that you need. And we'll draw their graphs. Let me go ahead and swap the page. Will give us two different functions. We'll do f of x equals 3 to the x and g of x equals 1/3 to the x. And we'll graph these by plotting points. Maybe let me add a little something extra here first. just to get us some practice with this stuff, let's first evaluate f of f of 1, f of negative 2/3, f of pi, and f of the square root of 2. So I know we can make a table, but the numbers we're going to want to plug into that table aren't likely to be numbers like these. And I just want to give you a feel for what happens when you start plugging in numbers like these. This we can do, but sometimes it's a little tricky. All right. What is f of 1?
Would it just be 3?
Yeah, nothing strange going on here. F of 1, since f of x is 3 to the x, this is 3 to the 1, which is 3. What is f of negative 2/3?
I can give you a fraction or a decimal, but I don't know what the fraction would be.
Well, so let's start with just this sort of statement, right? F of 1 is 3 to the 1, so f of negative 2/3 would be what? Well, it'd be 3 to the negative 2/3, right? And it's true that this is an irrational number. It's not a nice number. If you put this into your calculator, it will give you a decimal approximation, but not an exact value because calculators aren't very good with irrational numbers.
Isn't it one over the cube root of 3 squared?
Yeah, very nice. So that's the game here. We're going to take this and first, sorry, coffee's on the coffee table. First, we can take this and rewrite it as 1 over 3 to the positive 2/3. Right? A negative power moves the whole term downstairs. And then that 2/3 power we need to grapple with. So, and I'll remind you the rules for this, but the way this works is that the downstairs in this fractional power is a root, and the upstairs in this fractional power is a power. So this is 1 over the cube root of 3 squared. So that 2/3 power, you square the number and take the cube root. So this is 1 over the cube root of 9. And if you want to approximate how big this is, you can think about the cube root of 9. Now, 9 is not a perfect cube. 9 is a perfect square, but it's not a perfect cube. But it is nearby a perfect cube. What number close to 9 is a perfect cube?
Eight.
Yeah, 8. 8 is 2 cubed. So the cube root of 8 would be 2. So the cube root of 9 should be pretty close to 2, right? That's about as good as I can say. So this should be pretty close to 1 over 2, or 0.5. Now, if we want to know exactly, or we want to get a little better than, like, a little better than that, we can use a calculator. So 1 over the 9 to the 1/3, I'll write it like that, 0.48. And I'm using a shaky equal sign here. That means approximately equal to, because again, this is an irrational number, right? So the actual decimal expansion for this number goes on and on and on forever and ever and ever. But it's pretty close to 0.48, which, like we said, is pretty close to 1 over 2, because the cube root of 9 should be close to the cube root of 8, which is 2. All right, these next two are worse. F of pi, well, that would be 3 to the pi. And again, I can play some like games to get a feel for how big this is. We know pi is pretty close to 3, right? 3.14159, blah, blah, blah. So this should be somewhere around 27, right? Pi is close to 3. 3 cubed would be 27. So I expect this to be near 27, but if I want to be a little more precise than that, we're going to need some help from the calculator. So close to 27, yeah, 31.544. call it 31.54. F of the square root of 2 would be 3 to the square root of 2. The square root of 2 is about 1.4. And I don't have an intuitive idea of how big 3 to the 1.4 is, besides it should be bigger than 3 to the 1 and smaller than 3 to the 2. Maybe a little closer to 3 to the 1, because 1.4 is closer to 1 than it is to 2. But again, if we want, we can use a calculator, right? And your TI-30 can do all of this, no problem. So we'll call this about 4.7. Okay. These, like I said, are not the numbers I would choose to plug into a table if I was trying to draw a graph of this. But before I get to drawing the graphs of these things, I think it would be wise to remind you the rules you need to evaluate stuff like this, right? So the rules that we need to get from here to here are going to be pretty important for us, especially as we go towards solving equations and doing stuff with these functions. So let me remind you the rules for exponents, and then we'll come back to draw the graphs. And these are things that I'm sure you've seen in a previous algebra class, but if you don't use them, you forget them. So if I take a to some number and I multiply it by a to some other number, a to the b times a to the c, this is a times itself, b times, right? So a times a times a times a times a, b times. And this guy is a times itself, c times. So a times a times a times a, c times. If you write those two things next to each other, you've got a times a times a times a, b times, then a times a times a times a times a, c times. That is b plus c copies of a. So this is a to the b plus c. There's a corresponding rule for division. You take a to the b and divide it by a to the c. Upstairs, you've got a times a times a times a, b times. Downstairs, you've got a times a times a times a, c times. So you can cancel a bunch of the a's. You can cancel exactly c of them from the numerator, and you'd be left with a to the b minus c. This next one is a little less obvious, but perhaps the most useful for us. If you take a to the b and you raise the whole thing to the c power, so inside the parentheses you have a times a times a times a, b times, and then you're going to multiply that whole thing by itself c times, you're going to have a times a times a times a, b times, written down c times, which is b times c copies of a. So a to the b all to the c is a to the b times c. These rules work great and they're very intuitive if b and c are whole numbers, but they also work great if b and c are weird fractions or irrational numbers. These work fine for any real numbers, even complex numbers. There are some other rules. If you take a and raise it to the negative b, where b is any real number, this is one we used a minute ago, this is 1 over a to the positive b. So negative powers give you reciprocals. And then the rule that I'm going to share with you last here is pretty much only ever used when the powers are integers. So I'll write this with letters that usually represent integers. If you have a to the m over n, where m and n are integers, this is the rule we use to go from here to here. This is the nth root of the nth power of A. And because of rule 3, it turns out this is the same as the nth root of A, all raised to the m. And it's very rare we talk about roots that are like irrational numbers, right? So this n is pretty much always an integer. M could be any real number, but usually you see this rule applied with integers m and n. Maybe I'll put a sixth thing here, which is kind of a two-parter. A to the 0 is always 1. And 0 to the b is always 0. This assumes, though, that A is not itself 0, and B is not 0. So 0 to the 0 turns out is undefined in a weird way. And you'll explore that weird way in calculus. It's similar to why 0 divided by 0 is undefined. But these are the most important properties of exponents that we will be using through this chapter. Let's see, am I forgetting anything? I don't think so. This is good. So with this in mind, we now feel pretty comfortable, hopefully, evaluating stuff like this. If we wanted to approximate 3 to the pi better, we could think of pi as 22/7, right? That's a common approximation for pi, and that would be 3 to the 7th root of 3 to the 22. But certainly I don't know what those numbers are off the top of my head. So calculator is the way to go for most of these nasty things. But you do need to know how to get from like here to here. Okay, let's draw some graphs. So we want to sketch 3 to the x and 1/3 to the x. And this is going to lead us to talking about transformations. Now we're ready to do it. Let's plot some points. And let's use -2, -1, 0, 1, and 2 as the inputs. Those are fairly easy to work with. When x is -2, 3 to the x is 3 to the -2. What is that? As a fraction, please.
One over 9.
Very good. It's 1 over 3 squared, which is 1/9. When x is -1, we have 3 to the -1, which would be 1 over 3 to the 1, or 1/3. When x is 0, we have 3 to the 0, and remember, anything to the 0 is 1. When x is 1, we get 3 to the 1, which is 3, and when x is 2, we get 3 squared, which is 9. And you notice some kind of interesting symmetry in these fractions, right? That's why it's much nicer to write these as fractions than as decimals. I'm going to make a table for the other function here, and I'm going to do it in a different color. If you have another color, I recommend you do the same. The other function we wanted to graph was 1/3 to the x. And I'll use the same inputs, -2, -1, 0, 1, and 2. This one might require a little bit more thought. What is positive 1/3 raised to the -2nd power?
Would it just be a regular 9?
Yeah, exactly. So you take the reciprocal and then square. So this is the same as 3 to the +2, which is 9. And similarly, 1/3 to the -1 Well, now you're just taking the reciprocal and raising that to the first power. That's 3 to the 1, or just 3. 1/3 to the 0. Anything to the 0 is 1. 1/3 to the 1. Anything to the first power is itself. What about 1/3 squared?
One ninth.
Yeah, very good. That's 1/3 times 1/3, which is 1/9. And again, you might see some symmetry. So now I'm going to graph both of these functions, and I'm going to graph them on the same coordinate axis. Call this 1, 2, -1, -2. And we need to get up to 9, right? That's our largest output here, 9. And 1/3 of the way down would be 3. So somewhere around here would be 3. And 1/3 of the way to him would be 1. I'm not going to clutter the y-axis with the 1/3 and 1/9. We'll just do our best as we can. So in purple, I'll graph 3 to the x. When x is -2, 3 to the x is 1/9, which is teeny tiny, way the fuck down here. When x is -1, 3 to the x is 1/3. That one we can actually see, right? That would be 1/3 of the way up to here, which is like there. So somewhere around here. When x is 0, 3 to the 0 is 1. So that's my y-intercept. When x is 1, we get 3 here. And when x is 2, we're up here at 9. So the purple graph here looks a lot like the graph of 2 to the x, doesn't it? Same basic shape. And all exponential functions have this same basic shape. Going to grow really, really fast as we go off that way, and he's going to sit down on the x-axis really, really hard as we go this way. This is y equals f of x. And f of x is 1/3 of the x. I'm sorry, f of x is 3 to the x. In orange, I'll graph g of x, which is 1/3 to the x. When x is -2, g of x outputs 9. When x is -1, g of x outputs 3. When x is 0, g of x outputs 1. When x is 1, g of x outputs 1/3. And when x is 2, g of x outputs 1/9, which again is very, very small and hard to see over here. So the orange function is a graph looking something like this. He was sitting down very hard on that x-axis. So the orange function has a horizontal asymptote, which it approaches on as x goes off to the right. And the purple function has a horizontal asymptote, which it approaches as x goes off to the left. They both have the same domain and range as promised, right? Domain is all real numbers for both. Range is 0 to infinity for both. But what do you notice thinking about transformations about the orange and the purple?
Are they inverses?
Not
Kind of.
inverses. Remember, inverse functions are symmetric about the line y equals x. And that would give us a logarithm, which has a similar shape graph, but different. But what transformation would I have to apply to the purple to turn it into the orange? Think about like horizontal shifts, vertical shifts, horizontal scalings, vertical scalings. If I reflect this point over the y-axis, I get this point. If I reflect this point over the y-axis, I get this point. These are horizontal reflections of each other. All right, reflect over the y-axis of each other. Do you remember the algebra that signifies a horizontal reflection? If I want to flip the graph of f horizontally, what is the algebraic representation of that new function? Remember, if I wanted to shift f to the right by 5 units, this would be f of x minus 5. If I wanted to flip f over vertically, that would be negative f of x. If I want to flip f over horizontally, how do I do that?
Would it be f of negative x?
Perfect, perfect, perfect. Right, multiplying by a -1 on the inside is how you do a horizontal reflection. So then the question is this true? Right, from the graph, it looks like it should be true. Can we verify this algebraically? Your table is f of, so let's say g of 2. Is that the same as f of -2? Well, f of -2 is 1/9, g of 2 is positive 1/9. Yeah, so f of -2 is 1/9, g of 2 is 1/9. What about g of 1? Well, g of 1 should be the same as f of -1. Well, g of 1 is 1/3. F of -1 is 1/3. Yeah, this appears to be true. And if we wanted to, we can check this. F of -x, well, f of x is 3 to the x, so f of -x would be 3 to the -x. And by our rules for exponents, this would be 1 over 3 to the x. And g of x is 1/3 to the x, which by our rules for exponents is the same as 1 over 3 to the x, or 3 to the -x. Let me even just say it like that. This is the same as 3 to the -x by rules for exponents that we just shared. So yes, g of x is the same as f of -x. And we don't even need to write it as 1 over 3 to the x. It is true that 1 over 3 to the x is the same as 1/3 to the x, because 1 to the x over 3 to the x is the same as 1 over 3 to the x. But I think it's cleaner to see it this way. Okay. So yeah, these guys are horizontal reflections of each other. Right? That's what it looks like from the graph. And it's certainly true algebraically as well. There are special names. So all of your exponential graphs will have this same basic shape. There are special names for like the thing the purple is doing compared to the thing the orange is doing. Imagine you're a little guy walking along the purple graph from left to right. Is this going to be an easy walk or a hard walk?
A hard walk.
Yeah, this is going to suck. This is going to suck really bad because you're going uphill really, really steep all the time. In particular, this function you notice is always increasing. And we call this exponential growth, or a growing exponential. On the other hand, if I strap some skis to your feet and send you down the orange graph, and going from left to right, you're going to be hauling some pretty serious ass by the time you get over here. The orange function is always decreasing. And this is usually called exponential decay. So what is it about the algebra of G that makes it a decaying exponential? And what is it about the algebra of F that makes it a growing exponential? Turns out it's the size of the base. The base here, A, was 3, which is bigger than 1. And the base here, A, was 1/3, which is smaller than 1. So if your base is bigger than 1, put this down here. And this part with a fact. A to the x is a growing exponential if A is bigger than 1 and a decaying exponential if A is smaller than 1. Remember, the base is always positive, but it could be bigger than 1 or smaller than 1. Now, if A is exactly equal to 1, that's just going to be a constant function. 1 to any power is always just 1. That's kind of boring. But if your base is bigger than 1, then you're a growing exponential, and you will look like this purple graph. If your base is smaller than 1, you are a decaying exponential, and you will look like this orange graph. I'm going to share with you a little bit of nomenclature, and then I want to graph one more function. I'll let you guys go. So some terminology. Exponential functions. I'm going to start just abbreviating the word exponential with exp. Exponential functions are a part of a family of functions called transcendental functions. If you're taking trigonometry right now, then you have met a bunch of other transcendental functions. Sine, cosine, tangent, secant, cosecant, all of your trig functions are also transcendental. The word transcendental comes from the word transcend, which means to like grow beyond or to go above. In mathematics, it has a different meaning. Transcendental functions are functions which output transcendental numbers. So first, let me show you something really quickly here. All right, here's the calc book we use at both Santa Fe and at UF. James Stewart, Calculus, 8th edition. And you see right here, it says early transcendentals. What that means is that they're going to introduce functions like exponentials, sines, and cosines, transcendental functions, early on in the book. They're not going to wait because there are other ways to define these functions, right? You can define sine and cosine geometrically, like you are in your trig classes if you're taking trig, or you can define exponential functions as we have done here using algebra rules, or you can define them using some calculus operations. And what this early transcendentals means is that they start working with those transcendental functions right away, using the definitions that we're familiar with, using either geometry or algebra to define them. The reason they're called transcendental functions is because they often output transcendental numbers. And what are transcendental numbers? These are a special kind of irrational number. Which are not the root. I know I promised no more polynomial talk. Here's just a little reference to polynomial. Transcendental numbers are irrational numbers which are not the root of any polynomial with integer coefficients. So we've talked a little bit about rational and irrational numbers at the start of this course. The square root of 2 is an example of an irrational number, but it is not a transcendental number. Right? The square root of 2 is a root of the polynomial x squared minus 2. So while it is irrational, it's not transcendental. Those are called algebraic irrationals. Transcendental irrationals are numbers like pi and e. They're a little bit more special in the sense that they do not show up as the roots of any polynomials with integer coefficients. Proving that a number is transcendental is a fun challenge, and there's a lot of open questions in mathematics about whether this or that important constant is or is not a transcendental number. But I just wanted to share that with you because this is a terminology that you're going to run into when you take calculus. So exponential functions are transcendental functions. And that word means that they often output transcendental numbers. It also means that they're special, right? You can just think of it as very special. We love transcendental functions because they do cool shit. And one of the cool things they do is spit out these weird irrational numbers. Logarithms are also transcendental. Like I said, trig functions are all transcendental, and you'll meet a handful of other transcendental functions as you move through your calculus sequence. Okay, the last thing I want to do is graph one or two of these exponentials as a transformation. All right, we saw that like 1/3 to the x can be seen as a transformed version of 3 to the x. I think we have time for this, right? Yeah. Let's sketch function f of x equals 2 to the 1 minus x as a transformation of the parent function g of x equals 2 to the x. So all of these kind of basic exponentials, 2 to the x, 3 to the x, 5 to the x, these are now a part of our parent functions. I want to get this guy from this guy. So I need to figure out what transformations must be applied to this guy to turn him into this guy. And the trick to that is to do a little bit of algebra. My f of x here, 2 to the 1 minus x, can be rewritten ever so slightly as 2 to the negative x minus 1. If you change the order of subtraction, that's the same as factoring out a negative. This is a useful algebra fact in general. That a minus b is the same as negative b minus a. And we saw this back in transformation. That's good to revisit. So what are my transformations? How do I go from this guy to this guy? Well, I see a negative multiple on the inside, and I see a subtraction of a constant on the inside. So what are my transformations? Anybody tell me one?
One to the right.
Very good. There's a shift, a horizontal shift. I'm going to list this second, but shift 1 unit to the right. The other transformation is coming from this negative right here, and that's a horizontal reflection. So if I start with 2 to the x, which we graphed earlier, I know that 2 to the x looks roughly like this. Some points here, 0, 1, 1, 2, and 2, 4. And I reflect it horizontally. Then I will get this guy, which is 2 to the negative x. On his graph there, if I track those same points, 0, 1 will stay 0, 1. This will go to 1, comma 2 will flip over to negative 1, comma 2. And 2, comma 4 will flip over to negative 2, comma 4. And then finally, if I shift that to the right 1 unit, this will give me the graph I want. 0, comma 1 would move to 1, comma 1. Negative 1, comma 2 would shift to the right to 0, comma 2. And negative 2, comma 4 would shift 1 to the right to negative 1, comma 4. And the graph will look like this. And this is the graph I wanted. This is y equals f of x, which is 2 to the negative. The horizontal asymptote never changes. stays y equals 0 the whole time. But if I did any vertical shifting, any up or down shifts, that would change my horizontal asymptote. The bulk of your homework this week is going to be stuff like this, graphing transformations. There are plenty of evaluating functions. Basically all the examples we did here today. You're going to see stuff like that in your homework. The big goal for this section right now is to get you to a place where I can give you a exponential function and you can picture its graph readily, right? You know right away what that graph looks like. Next time, we're going to talk about the number e. Look at some applications, some real world problems that involve exponential functions, and you'll see how that kind of gives rise to this number e, which, by the way, is a transcendental number. After that, we're going to talk about the inverses to these exponential functions, which are called logarithms, and then we'll see how to solve equations using logarithms. I know this is something that a lot of people struggle with back in college algebra or in high school algebra 2, wherever you introduce this stuff. And it's possible to kind of sneak your way through those classes without getting comfy with these. We have one whole test just built on exponentials and logarithms, nothing else. That is going to be your exam 3. So it is not possible to sneak through this class without getting comfy with these things. If you take the time, you will get comfy, I promise. Remember, exam 3 is coming sooner than you think. Exam 3 is very, very close already. It's a small chunk here. So please put the time in and work on the homework. If you get stuck on anything, don't hesitate to ask for help. And that's it from me. So I will see you guys next Tuesday.
Thank you.
Real quick, before we go, if you did not take the test on this Tuesday, if you missed the test for whatever reason, please come to my office hour on Friday at 1 p.m. I do have a group of people taking a makeup test then, and I really don't care why you missed the test, but if you didn't take it, I want you to take it. Please come to my office hour Friday at 1. All right, that's it. Bye, guys.
I have a question.